ಸರ್ ಹೇಳ್ರಿ ಹೇಳ್ರಿ. ಇಲ್ಲ ಆಡಿಬಲ್ ಇಲ್ಲ ಸರ್. ಇಲ್ಲ ಸರ್. ಅಲ್ಲ ಓಪನ್ ಐತಿ ನಿಮ್ದು ಹತ್ರ ಬರ್ಬೇಕ್ರೆ ಹೆಂಗ್ ಸರ್? ಇಲ್ಲ ಸರ್ ಇಲ್ಲ ಸರ್. ನಿಮ್ದು ಆಡಿಬಲ್ ಇದು ಆಡಿಯೋ ಓಪನ್ ಐತಿ ಸರ್ ಈಗ. ಬಟ್ ನೀವು ಮಾತಾಡಿದ್ ಕೇಳೋದು ಅಷ್ಟೇ ಸರ್.
ನೋಡು ಈಗ ನೋಡಿ, ಈಗ ವಾಲ್ಯೂಮ್ ಜಾಸ್ತಿ ಮಾಡೀನಿ. ಬಂದದೆ ಬಂದ್ ಮಾಡ್ಬಿಡ್ಲಿ ಹಂಗ್ರಿ ನಮ್ಮ ಮೊಬೈಲ್.
ಸರ್ ಮಾತಾಡ್ರಿ.
ಹಲೋ ಹಲೋ.
ಹಾ ಕೇಳಿಗಿದೆ ಸರ್ ಕೇಳಿಗಿದೆ.
ಕೇಳಾಗತೈತಿ?
ಹಾ ಸರ್ ಹಾ ಸರ್. ಓಕೆ ಸರ್ ಡನ್. ಡನ್ ಸರ್. ಸರ್ ನಿಮ್ದು ಫೇಸ್ ಯಾಕೆ ಕಾಣ್ತಿಲ್ಲ? ಕತ್ಲಾಗೈತಿ ನಿಮ್ ಮುಖಕ್ಕೆ.
ಅದು ಮತ್ತೆ ಜಾಯಿನ್ ಮೀಟಿಂಗ್ ಅಂತ ಬರ್ತದಲ್ಲ.
ಅಲ್ಲ ಸರ್ ನಿಮ್ ಮುಖಕ್ಕೆ ಯಾಕೆ ಕತ್ಲು ಕಾಣತೈತಿ? ಮುಖ ಕಾಣೋದು ಕರೆಕ್ಟ್ ನಿಮ್ದು.
ಈ ಕಡೆ ಆಯ್ತು. ಈ ಕಡೆ ಮುಖ ಡೈರೆಕ್ಷನ್ ಚೇಂಜ್ ಮಾಡ್ಕೊಂಡು ಕುಂಡಿರ್ತೇನೆ ತಡಿ. ಮುಖ ಮಾಡ್ಕೊಂಡಿರ್ತೇನೆ. ಈಗ ನೋಡು.
ಎಸ್ ಸರ್ ಡನ್ ಸರ್. ಸರ್ ಕ್ಯಾಮ್ರಾ ಸ್ವಲ್ಪ ಕ್ಲೀನ್ ಮಾಡ್ರಿ ಸರ್. ಅದ
ಕ್ಯಾಮ್ರಾನ
ಸ್ವಲ್ಪ ಸ್ವಚ್ಛ ಮಾಡ್ರಿ ಸರ್. ಯಾಕೆ ಕಾಣೋದು ಯಾಕೋ ಕ್ಯಾಮ್ರಾ ಸರ್. ಇಲ್ಲೇ ಮೇಲೆ ಇರುತ್ತೆ ನೋಡಿ ಸರ್.
ಬೆಳಕ್ ಸರಿ ಈಗ ನೋಡು.
ಸರ್ ಕ್ಲಿಯರ್ ಇಲ್ಲ ಸರ್.
ಕ್ಲಿಯರ್ ಇಲ್ಲ.
ಹಾ ಇಲ್ಲ ಸರ್.
ಒಟ್ಟಿಗೆ ಚೇಂಜ್ ಮಾಡ್ತೀನಿ.
ಹಲೋ ಮೇಡಮ್. ಇಲ್ಲೈತಿ ಸರ್. ಬಾಳ ಕಪ್ ಕಾಣತ್ತೀರಿ ಸರ್.
ಬೆಳಕಿಲ್ಲ.
ನಿಮಗೆ ಕಾಣ್ತದೆ ನೋಡಿ ಸರ್. ಅಲ್ಲಿ ಒಂದು ಇದೆ ರಿವ್ಯೂ ಕಾಣ್ತದೆ ಸರ್.
ಇಲ್ಲ
ಸರ್. ಇಲ್ಲ ಸರ್ ಇಲ್ಲ ಸರ್. ಬ್ಲರ್ ಕಾಣದ ಸರ್ ಯಾಕೋ ಮುಖ.
ಈಗ
ಓಕೆ ಸರ್.
ಇರ್ಲಿ.
ಬೆಟರ್ ಸರ್. ಬೆಟರ್ ಐ ಸರ್. ಓಕೆ ಸರ್.
ಅಲ್ಲ ಬರೀ ಸೆಟ್ಟಿಂಗ್ ಮಾಡಿದ್ರೆ ನೀವು ಟೈಮ್ ಎಷ್ಟೊತ್ತು ತಗೋತೀರಿ? ರೀಡಿಂಗ್ ತಗೋರಿ, ಸ್ಟಾರ್ಟ್ ಮಾಡ್ರಿ.
ನೋಡ್ರಿ 20 ಇರ್ತಕ್ಕಂಥ ನ್ಯಾಷನಲ್ ಸೈನ್ಸ್ ಡೇ ಕರೆ ಒಂದೇನು ಅವು ಎಕ್ಸಾಮಿನೇಷನ್ ಪೀರಿಯಡ್ ಅದು ನೋಡ್ರಿ ಬಟ್ ಸಮ ಮಂಡೇ ಐತದ ಮಂಡೇ ಈವ್ನಿಂಗ್ ಅರ ಮಾಡಿ ಮಂಡೇ ಸಿಸ್ಟಮೆಟಿಕ್ ಆಗಿ ಮಾಡಿ.
Hello. Hello.
ಹಲೋ ಸರ್, ಇನಾಮದಾರ್ ಸರ್, ನಮಸ್ಕಾರ ರೀ.
ನಮಸ್ಕಾರ ರೀ.
ನಮಸ್ಕಾರ ಸರ್, ನಮಸ್ಕಾರ. ಹೆಂಗಿದ್ರಿ? ಆರಾಮದ್ರಿ ಸರ್?
ಆರಾಮ್ರಿ. ನೀವ್ ಹೇಗಿದ್ರಿ? ನಮಸ್ಕಾರ.
ಬಹಳ ಖುಷಿ ಆಯ್ತು ಸರ್ ನಮಗೆ.
Thank you so much for inviting.
Yes, sir. It is our great pleasure, sir.
Yeah, it's good. ಯಾಕಂದ್ರೆ ನಿಮ್ ಕಾಲೇಜಿಗೆ ಬನ್ನಿ ಬರಕ್ಕಾಗಿಲ್ಲ, ಇವತ್ತು ಭೇಟಿ ಆದಾಗ.
ಹೌದು ಸರ್, ಅವತ್ತು ಸ್ವಲ್ಪ AC ಮೀಟಿಂಗ್ ನೀವೇನು ಬಿಸಿ ಆಗ್ಬಿಟ್ರಿ ಅವತ್ತ. AC ಮಾಡ್ಕೊಡಿ ಸರ್, ಇನ್ನೊಂದು AC ಕರಿತೇವೆ ಅವ್ ಬರುತ್ತೆ.
Okay. But unfortunately, just now I received a message. ನಮ್ಮ elder brother expired ಅಂತ. So tonight I have to leave to Bangalore. Lecture ಮುಗಿಸಿ.
ಹೌದ್ರಿ ಸರ್, ನಿಮ್ಮ ಓನ್ ಬ್ರದರ್?
ನಮ್ಮ eldest brother.
ಹೌದ್ರಿ ಸರ್?
Yeah.
ಅಯ್ಯೋ, ಸಾರಿ ಸರ್.
ಒಂದು ಈಗ half an hour ಆಯ್ತು, ಅದಕ್ಕೆ ಲೆಕ್ಚರ್ ಮುಗಿಸಿ ಮತ್ತೆ ಆ ಕಡೆ ಹೋಗಿ.
ಹೌದ್ರಿ ಸರ್? ಅಯ್ಯೋ ಸಾರಿ ಪಾಪ. ಎಲ್ಲಿ ಬೆಂಗಳೂರು ಇರ್ತಿದ್ರಿ ಸರ್?
ಹ್ಞೂ, ಬೆಂಗಳೂರಿಗೆ ಇರ್ತಿದ್ರು.
ಹೌದ್ರಿ, ಅಯ್ಯೋ ಪಾಪ. ಗೋರ್ಪಡೆ, ಹಲೋ ಗೋರ್ಪಡೆ.
ಹಲೋ ಸರ್, ಸ್ಟಾರ್ಟ್ ಮಾಡ್ರಿ.
ಸರಿ, ಸ್ವಲ್ಪ ಪ್ರಾಬ್ಲಮ್ ಆಗಿದೆ, ಅವ್ರು ಜಲ್ದಿ ವಾಟೆಡ್.
ಇಲ್ಲ, ನೋ ಪ್ರಾಬ್ಲಮ್. ಇದು ಯಾರು ಫೋನ್ ಮಾಡ್ತಾ ಇದ್ರು?
ಆಯ್ತು.
Good afternoon all. I Santosh P. Gorpade, assistant professor in the Department of Physics. I welcome you all for this one-day national level online seminar on photonics and its application. I welcome you all. Now, as per the agenda, now I request our honorable principal, Dr. L.D. Horker sir, to welcome the audience as well as to welcome our today's resource person, Dr. Sanjeev R. Inamdar sir. Now over to Dr. L.D. Horker sir. Sir, please.
Okay. Thank you. Please, thank you. So on this occasion of organization of national level online seminar organized by Postgraduate Department of Studies and Research in Physics of our college, so on photonics and its applications. So on this occasion, we are very much having Dr. Sanjeev R. Inamdar sir, Professor, Department of Physics, Karnataka University, Dharwad, with us now. So sir has already joined. So Dr. Inamdar sir is an intelligent student, an excellent researcher, a very young, fascinating teacher, a good administrator also, above all, a gentleman academician, Professor Sanjeev Inamdar sir. So on behalf of our college staff and students, I extend a warm and sincere welcome to you, sir. Welcome you, sir, Inamdar sir.
Thank you so much, sir.
Welcome, sir. Welcome. Please, yes, sir.
Thank you.
Please. Yes, sir.
Yeah.
And I extend a warm and sincere welcome to all the delegates who have joined this online seminar and faculty, and I extend warm welcome to all my student friends who have joined this seminar, who are going to be benefited by Dr. Inamdar sir's speech on photonics and its applications. So with this, once again, welcome you all. Thank you. Thanks a lot, sir.
Thank you, sir. Thank you so much for wonderful welcoming the gathering and as well as the resource person, Dr. Sanjeev Namdar. Thank you so much, sir. Now I request our sir, S.V. Angadi, sir, Associate Professor, Department of Physics, to introduce the resource person. Now over to S.V. Angadi, sir. Sir, please, sir.
Good afternoon, everybody. Respected Dr. S.R. Inamdar, sir, Professor, Department of Physics, Karnataka University, Dharwad, beloved Principal, Dr. L.D. Varkeri, all the learned colleagues, delegates, and dear student friends. It's give me a great pleasure to introduce Dr. Sanjeev R. Inamdar, sir, resource person for the national level seminar on photonics being organized by the PG Department of Physics, is PC Jabin Science College, Hubballi. Dr. Sanjeev R. Inamdar, sir, is an elected fellow of Royal Society of Chemistry and an elected fellow of Karnataka Science and Technology Academy, Government of Karnataka, Bangalore. He is one among the first batch students to pass the CSIR National Entrance Test in the year 1983 and was awarded CSIR JRF in the year 86 and CSIR SRF in the year 89. He worked on dye lasers, ETDLs, for his PhD. Sir is a DRDO research associate and conducted research on ultra-fast spectroscopy at Karnataka University using pulsed lasers, conducted pump probe experiment and measured ground state repopulation times of laser dyes with a resolution of 50 ps. Dr. Inamdar sir has successfully guided 5 PhD students on the topic of rotational dynamics of laser dyes and 8 students on FET sensors using nanoparticles and laser dyes systems. He conducted a novel frequency upconversion experiment using laser based on 3-wave mixing phenomena and studied the finer details of solvation dynamics of laser dyes, with which was the first experimental report of its kind from India in the year 1995. Sir has a rich research experience in experimental research on lasers and fluorescence spectroscopy of nano and biomaterials. He has published 100 research papers in international and national journals of repute and has delivered lectures before international academia. His H-index is 20 and citation index 1493. He guided 15 students of PhD, 6 for MPhil degree, and currently he is guiding 8 PhD students. Dr. Inamdar sir successfully collaborated with the scientists from CNES and University of Paris, France, and ISRO India, carried out international collaborative research as part of Indian Ocean Experiment projects from 98 to 2001 to monitor pollution in Indian Ocean using LIDAR and other equipments. And before I conclude, such a wonderful and resourceful person is going to deliver and enlighten all our students and faculty on the topic photonics and its applications. I expresses my great sense of gratitude to the organizer for giving me this opportunity. And once again, I welcome you, sir, on behalf of our department. Dr. Inamdar, sir.
Thank you, sir. Thank you.
Thank you so much for sir for your wonderful the introduction of resource person. The resourceful person is our resource person, Dr. Sanjeev R. Inamdar, sir. Now, I request Dr. Sanjeev Inamdar, sir, to proceed the lecture, sir. Sir, over to Inamdar, sir.
Yeah. Hello. So, am I audible?
Yes, yes, sir.
Yeah. So, very good afternoon to all of you. my dear friend, Professor Parkere, Principal of PC Jabin Science College, and all the staff of MSc Physics, Professor Pujar, Dr. Jirgar, and all others, and my dear students. It gives me a great pleasure to be with you to share some of the ideas about the latest topic, that is photonics. Hope I am audible. I'll just share my screen now.
Yes, sir, you are audible. Sir.
Yeah. Is it visible?
Yes, sir, it is visible, sir.
Yeah. Please let me know if the slides are changing or not. So
Yes.
do you see the screen now?
Yes, yes, sir. Yes, sir, it is visible, sir.
Yeah. Okay. So the title of my topic is Photonics and its applications. So let me start this talk by the Sanskrit Loka Guru Brahma, Guru Vishnu, Guru Devo Maheshwara, Guru Sakshat Parabrahma Tasmai Shri Guruve Namah. With deep respect, I bow to my teacher, Professor M.I. Savdati, who introduced me to this wonderful and colorful field of light, lasers, and photonics. So here you see of my mentor, my guru, Professor Savdati, and along with him, another one of my teachers, Professor Mulimani. So to start with, let us know what is photonics. Photonics is a brand new term with few years of history. And photonics is nothing but the science and technology of light, which includes everything about light, generation of light, detection of light, and manipulation of photons through emission, transmission, modulation, signal processing, and switching, amplification of light, and sensing of light. And most of the photonics applications occur in the visible range as well as near infrared range of the electromagnetic spectrum. So since most of the audience are students of physics, I believe everybody is aware of the electromagnetic spectrum, which covers from gamma rays to radio waves. Photonics is a field which can be called as an outgrowth of the first practical semiconductor light emitting device, that was semiconductor lasers, which was invented in the early 60s, and the invention of optical fibers, which happened in the early 70s. So just to refresh you, this is the electromagnetic spectrum. We have all kinds of frequencies here, starting from few hertz to the largest value around 10 to the power of 25 hertz. We start from radio waves and go up to gamma rays with increasing frequency. And in this entire spectrum, we have a very tiny range of wavelengths or frequencies which are visible to the naked eye. And this visible spectrum covers wavelengths from 400 nanometers to 700 nanometers, starting from indigo to red. So you are all aware of the complete visible spectrum, which covers all the colors with pure, and that forms a very, very tiny spectrum. And beyond this red region, we have infrared, and beyond the violet or indigo region, we have ultraviolet, which are highly energetic. So we have all kinds of light sources to generate the entire range of frequencies. And some of the typical light sources are incandescent bulbs, arc lamps, and the recent light emitting diodes, and the most powerful source of light, which are lasers. And as you all know, laser is an acronym for light amplification by stimulated emission of radiation. And laser is, to tell you frankly, as old as me. So it was invented in 1960, and in 2010 it celebrated Golden Jubilee, and in 2020 celebrated 60 years. And from the last few years, UNESCO has started celebrating May 16th as International Day of Light to commemorate the invention of the first laser by Theodore Neumann, whose picture you can see here, who invented the ruby laser. On May 16th, 1960, this laser was demonstrated in the US. So a brief history of laser. As I said, May 16, 1960, first laser was demonstrated by Theodore Neumann, and that was the ruby laser, which was pumped by an energetic flash lamp. And in the same year, Ali Jawan invented the gas laser, that is helium near laser. As you know, ruby laser was a solid state laser. In October 1961, we had another powerful laser, that is neodymium glass laser. And in December 1961, immediately this laser beam or laser light was put to use of the society. That was the first medical use of this laser in ophthalmology was demonstrated by destroying retinal tumor using the laser. And in 1962, welding of springs in watches could be done. As you know, in the 60s, we had no digital watches. We had spring watches, and they were quite tiny, and welding or repairing those things was quite difficult. So tiny laser beam was used for welding these springs. 1962, we had semiconductor diode laser, and also neodymium YAG laser was invented. 64, pulsed argon ion laser was invented. Also, the most powerful carbon dioxide laser was invented. And in 1966, we had another important lasing action was demonstrated in a liquid dye laser. And the specialty of this was multicolor, because most of the lasers have a single wavelength emission, whereas the dye laser can emit simultaneously a range of wavelengths, because we are using a fluorescent dye as a laser medium. And this can be tuned by using a grating or a prism. In 1970, an excimer laser was invented. And immediately after this, the series of applications of laser beams began to come out. The first commercial development of optical fibers was done in this year, 1970. So optical fiber communication idea was mooted in that year. In 1974, Wrigley chewing gum became the first product to use the barcoding. And barcoding, we are all familiar, because if you go to all malls and more shops, you commonly see this at the counter. 1976, we had free electron laser, and in 77, the actual practical optical fiber communication system was installed in Chicago. And we are all familiar with CDs and DVDs. In fact, first it was invented in 1977, but it failed to launch because there were several technical problems. In 78, again, Philips launched the first compact disc, and in 1982, first audio CD was brought out. And this audio CD, it is not comparable with the present CDs, because this audio CD could hold hardly 2 to 4 songs in one CD. In 1994, we had quantum dot laser or semiconductor quantum dot laser. Then 2003, the first laser-powered aircraft was demonstrated. In 2010, high peak power laser was demonstrated. And in 2020, recently, the highest power laser, that is petawatt laser, which is called Hercules, was also demonstrated. 10 to the power of 15 watts per square centimeter. So we have all kinds of lasers operating in the entire spectrum, operating at variety of frequencies. And laser, people, when it was invented, people used to call it a solution in search of problems because it was used to as many applications as possible. So this is the picture of Omega laser built in 2020 to study nuclear fission. And this is the recent one, that is a petawatt or 10 to the power of 15 watt laser built in 2020. And if you want to look at a typical system, this is a 500 terawatt laser, which is being developed at the University of Michigan College of Engineering. So you may be surprised to know that photonics applications cover a wide range. It's used in scientific research like physics, chemistry, biology, biotechnology, optical computing, almost any branch of science. Then laser-induced background spectroscopy, atmospheric remote sensing, nonlinear optical phenomena, then laser-based light detection and ranging, which is called LiDAR. Then in industry for cutting, welding, marking, barcode reading, etc. Then in medicine for surgery, photodynamic therapy of cancer, and in defense as well as in holography. So just a couple of slides to give you some idea of what a laser is and how it is different from the ordinary light. So on the left, you can see the light from an ordinary incandescent bulb, and we see that it emits all colors. So ultimately it appears yellowish white. So it contains many wavelengths and all the photons are emitted in all the directions. So if you put a bulb in your room, it illuminates the entire room because it is traveling in the light. Photons are traveling in all directions. So therefore it is multidirectional, contains many wavelengths. And since the photons emitted by this bulb do not have any phase correlation with one another, it is incoherent light. On the right, we see laser and laser beam. We see that it gives always a monochromatic radiation, that is a single wavelength or single frequency. Suppose if you take a helium neon laser, it always gives you 632.8 nanometer, that is red light. And if you take an argon ion laser, then it can give you 488 nanometer blue light or 514 nanometer green light. So likewise, all the lasers will give only one wavelength. So therefore it is called monochromatic, and the beam is highly directional because you might have seen the people using the laser pointers for games as well as for presentation of talks, etc. You see that it always travels in one direction. Okay, and this is coherent because all the photons emitted by this source will be having certain phase relation. So monochromatic, directional, and coherent, and moreover, the laser output is highly intense. For example, if you take a tiny 1 milliwatt helium neon laser output, it is at least 10 to the power of 7 times brighter than the sunlight. So therefore, it is hazardous to put light directly into the eye. So it can instantaneously damage the retina. So whatever be the laser, whether it's a gas laser, solid state laser, or liquid laser, or a semiconductor laser, there are three essential parts that a laser should contain. First is active medium. And active medium, by active medium, I mean it's a collection of atoms, molecules, or ions, which can be excited to a metastable or long lifetime energy level by an energy source. Okay, so it could be, the active medium could be solid state crystals like ruby or NdR, or it can be fluorescent dyes as in liquid dye lasers, or it can be carbon monoxide or carbon dioxide or helium neon or nitrogen gases in case of gas lasers, and semiconductor like GAS, GaNP, etc. in case of semiconductor diode lasers. So all these form active medium. And for this active medium or collection of atoms, we need certain energy to pump them or to excite them to higher energy level. Therefore, we need some kind of excitation or pumping mechanism. And depending on what is the active medium, we have three basic methods of excitation or pumping. One is optical pumping, like a flash lamp. Another is electrical pumping, like an electric discharge, which is used in helium neon laser, or a chemical reaction. And the third and most important component is an optical feedback. Just like electronic feedback, we use optical feedback here by simply placing two mirrors at the end of the active medium. And one of them is highly reflective, which can be 100% mirror, reflecting mirror. And the other one can be a partially reflecting mirror with extremely small amount of transmission, which will allow the laser light outside of the active medium. And these are the three important processes that are happening in the laser. The first one, on the extreme right, we see a figure where we have a ground state and excited state, and there is a photon which is incident on the material, which takes an atom to the excited state E2. That is figure C, which is called the absorption process. So whenever light falls on the material, it immediately absorbs and the atoms or molecule go to the excited state. The second one, coming to figure A, this excited state E2 can have certain excited state lifetime or radiative lifetime. For example, 2 nanoseconds, and after these few nanoseconds, immediately the system will relax on its own to the ground state. And this extra energy is given away as a photon with energy Helium. So this is a spontaneous emission, and sometimes it's also called fluorescence. Coming to figure B, let us say that already the atom is in the excited state E2. And when it is there in the excited state E2, if you put one more external photon with the same energy h nu, which is equal to the energy difference between E1 and A2, this photon does not have any atom in the ground state for absorption. Therefore, it simply passes through the system. While passing through, it will stimulate the atom in the excited state E2 to just relax to the ground state by emitting the photon. So you have one photon that is emitted from E2 and another photon which is stimulating photon. So you have now two photons. But therefore, this kind of process is called a stimulated emission, and this is the process which is responsible in generating the amplified stimulated emission in case of all the lasers. Okay, so let us forget about this scheme. Yeah, so this is how it happens. So first we will see on the top, we have a collection of atoms, and at the end we have two mirrors. One is high reflection, another is output coupler or partially reflecting mirror. And when we give pumping energy like electrical or optical, some of them go to the excited state, and after a certain time or excited state lifetime is over, slowly these excited atoms will emit photons, and these emitted photons are spontaneously emitted photons, so they are going out in all directions, and some of them travel parallel to the system and reach the one of the mirrors. And once they hit the mirror, they come back into the system, and on the way in the system, they act as external photons because they have the same energy, and they will stimulate some of the already excited photons to release the energy. So therefore, the number of photons will go on doubling. So two photons can stimulate two excited atoms, so the number of emitted photons will be 4. And this kind of thing happens until they reach the end of the cavity, and finally they reach the back mirror, and again they will go back into the system. Whereas those photons which are going out of the system will be lost, and therefore spontaneous emission will reduce. So such kind of reflections between back and front mirror, they happen nearly billions of times, so that almost all the atoms in the system will go to the excited state, and most of the emitted photons will be stimulated emission. And when the system is saturated, some of the photons will be released or transmitted through the output coupler, which is a partially reflecting mirror, and this comes out as useful laser beam. So a typical laser, this you might have studied, because I think this appears in your SSLC, PUC, and BSc books. This is a helium neon laser schematic diagram. So we see the tube which contains helium neon gas mixture, and this particular laser, neon is the active medium and helium supports it as a matrix, and the laser beam comes out from the neon energy levels. And this is filled in this porous tube at low pressure, and then we have cathode and anode, between which we supply DC power supply and strike a discharge. So you will be able to see a pink glow in the beginning, and then once the amplification takes place, you will see the laser output which is coming out at the red color 632.8 nanometer, exactly a single wavelength. And here you see that you can almost generate laser radiation from 193 nanometer, 0.193 micrometer, or 193 nanometer, which is in the ultraviolet. And you can go up to 10.6 microns for the carbon dioxide laser. So you can cover from deep ultraviolet to far infrared. And some of the popular lasers here are nitrogen laser, which produces 337.1 nanometer in the UV, then argon laser at 488 nanometer, that is blue, then Nd:YAG laser, that is 1.064 in the near infrared, and 633 for helium neon. And lasers can generate output or laser beam in two ways. One is continuous wave output, that is the energy of the laser beam will be constant as function of time. And you can also have pulsar lasers. So these pulse lasers will be giving pulses just like a flash lamp. So there can be 10 pulses per second, 100 pulses per second, or 10 to the power of 6 pulses per second, that is megahertz lasers also are possible. So with this, we'll see some of the applications of lasers, because as I said, photonics is the science and technology of light and its utility, the generation of light, detection of light, manipulation of light, and utility of light in various applications. So this was the earliest, most important thing that was discovered. So during World War II, there was a need to take pictures of the missiles. That means there was a need to build ultra-fast cameras. So present-day cameras can capture moving items, but in those days it was not possible. So a technique was developed by Eigen, Norrish, and Porter, who later won a Nobel Prize in Chemistry for this invention. So this is basically a pump-proof laboratory technique wherein a chemical sample is first excited by a strong pulse of light from either a flash lamp or a nanosecond or picosecond or femtosecond laser. And once it is excited by such a light source, it goes to the excited state. Then you use another laser, another light source to study the population distribution of this system. So once the pump light excites all the atoms or molecules in the system to the excited state, there will be redistribution of the atoms in the ground and excited state. So you can set another beam with weaker energy to study. That is, either you can study absorption or transmission and look at the population distribution. And the importance of this technique is you can use any detector like a photomultiplier or a photodiode, but the sensitivity of the system is not limited by the response time of the detector, because ultimately it depends on the pulse width of the source. For example, if you are using a picosecond laser for such technique, then it is possible that your detection can be in the range of picoseconds. So therefore, ultra fast cameras could be built using this technique. So this is a typical technique. Here we see the pulse laser here, which can be a picosecond or femtosecond laser, which excites the sample here, and its job is over. So once it is excited, its job is over. So your shutter can close this, and this sample will be having excited as well as grounded population distribution. Now use a xenon lamp here through optical fiber and set that light through this sample and study its transmission or absorption characteristics. So based on this flash photolysis technique, also people are also using pump probe methods in the laboratory to study orientation relaxation in the fluorescent dyes in order to look at the solute solvent reactions, etc. The basic reason for the use of this is response time of the detector becomes unimportant, and the fastest pulse can give you the better results, because molecular rotations in liquids can happen as fast as few picoseconds. So therefore, a picosecond laser will be useful here. So this is the typical diagram. So here we see a pump pulse again. And this sample, that is a liquid sample, you pass it through this and it sends most of the molecules to the excited state. Then use a weaker probe pulse from the same laser and you can introduce delay. That means you can study the spectrum transmission or absorption spectrum as function of time after allowing the probe pulse by delaying it for a few picoseconds, like 33, 66, etc. Because 1 millimeter distance amounts to 33 picoseconds of time delay. So that is how it is detected. And you can use any simple normal detector like a PMT or a simple photodiode, because it is not important for us whether it is having a fast response time or not. So based on this, we can also use polarized light pulses. We can also use the polarized light pulses in order to look at the molecular rotation in solution. Suppose if you have solution and a colored substance in that, colored fluorescent substance, then you can use a polarized light or polarized laser beam for excitation, and the molecules which are oriented along the direction of polarization of the excited light will be selectively excited in this, and all those molecules which are not parallel to that, they will remain unexcited. So we are creating a situation that certain molecules are excited and certain other molecules with other directions are unexcited. So we are creating some kind of polarization anisotropy. And this polarization anisotropy will relax or can decay by molecular rotation. And this molecular rotation will depend on the properties of the solvent, especially the solvent viscosity. So therefore, by measuring these transmissions using polarized laser beam with polarized parallel and particular excitation polarization can give you idea about the rotation reorientation time. for example, we can get results like this. Suppose if you are using a series of solvents like methanol to decanol, which are increasing in their viscosity, we see that the rotational of the molecule will directly depend on viscosity here, theta. So therefore, you can see that it is directly proportional to this. So experimentally, one can measure. And if you look at this table, which we have done in our laboratory, the viscosity of these series of alkanes is from 0.2 to 3.03 millipascals or centipoise, and we see that the orientational relaxation time varies from 81 picoseconds to 1156 picoseconds. So this is one of the very popular technique used in ultra-fast spectroscopy. So for the time being, we skip this. Yeah, another use in photonics of lasers is in communication. So you are all aware of the communication, and right now I am communicating with you. You are watching my lecture, and everybody is using broadband connection or mobile connection, etc. And this is all happening because of optical fiber communication. Okay, and optical fiber communication can be said as a perfect marriage between the diode lasers and optical fibers, because the diode lasers were invented in the 60s, and nowadays you see a very tiny diode lasers available in the market, and the beam size is also quite small, but the light is quite intense, and you still get coherent and monochromatic light. And the optical fibers, when they were invented in 1970s, they were having a loss of 1000 decibels per kilometer. But nowadays, the loss in the optical fibers is less than 0.01 decibels per kilometer. And the production of optical fibers is also quite cost effective. Therefore, there is a perfect match between these two components. So therefore, optical fiber communication has been very, very popular. So this is a typical laser diode, as you see. That's quite small, and within this there is a laser diode, and there is also a photodiode which detects a light emitted by that, and it also gives some kinds of electronic feedback so that the output remains constant. And these are the cross sections of the red and helium, red and green laser pointers, which are commonly used for presentation. Yet they give very powerful light. And this is the cross section of optical fiber. You are all aware of that the light travels through the optical fiber by total internal reflection. So light which enters the core at a particular angle does not get lost in the cladding, and it keeps on traveling until the end of the fiber. And this can be clearly demonstrated using a simple green laser pointer using a glass slab or a glass cylindrical rod. So you clearly see the beam, how it passes through this, which suffers the total internal reflection. Absolutely no beam is going out of the wall. Okay. And also it is possible to use laser for frequency doubling and frequency doubling. Okay, so here we are passing the 1064 nanometer radiation from the Nd:YAG laser through a nonlinear optical medium, so which converts that into half of the wavelength or double the frequency, which we call second harmonic or 2 h cross omega. So this is a little bit complicated system, so it requires a lot many components and perfect alignment. And this was another experiment we did, but anyway, we'll skip that. So there is another thing which is very useful regarding laser, that is laser induced fluorescence. So just like we use mercury lamp or any other ultraviolet light source, laser also can be used as an excitation source for laser induced fluorescence. For example, this one of the dyes, fluorescence, which has maximum absorption at 490 nanometer, can be best excited by an argon ion laser, which produces blue-green, that is at 488 at blue range and 514 nanometer green. And this could be done for fluorescence imaging, like this is the neuron network. So this is excited by green laser of the argon ion laser, green beam, and this can be watched under the microscope. So totally no background is visible here. These are some of the medical applications. The top one is for stain removing from the skin. The second one is tattoo removal, where they are using a carbon dioxide laser. And the bottom one is laser breast biopsy, where they are using again high power carbon dioxide laser, which cuts the tissue as well as it also seals the tissue during the surgery so that there is no blood loss. And here also second one is used for angioplasty or treating the laser angioplasty, where they are using NDR laser. And the last one, which is used in case of diabetic retinopathy, where retina is damaged due to high blood sugar. So argon ion laser can be used for repairing that. So as I mentioned, dye laser is also has also been one of the most powerful and most popular laser, and it was invented in 1966. And the active medium is a liquid dye here, and which produces a wide range of wavelengths. So here you can see at the center we have a cuvette here, wherein we are keeping rhodamine 60% dye, and it is excited with 488 argon ion laser. And it is emitting in the range of yellow orange, that is at 580 nanometer. So this is another picture. Now light also can be used to detect and range. So just like we have radar, radio detection and ranging, this light detection and ranging is called LiDAR. So where we are using a powerful laser and shine it towards the sky, and the particulate matter in the sky or in the atmosphere, which are called aerosols, they can absorb this or scatter this radiation, and can be detected, and you calculate the time of flight between the laser to the particulate matter and to the detector, so that you can precisely calculate the distance of the object from the laser. And also it is possible nowadays that you can get the clear spectrum of the particulate matter in the atmosphere and what is the content of that. For example, this is the atmospheric spectral transmission, which shows that what are the things present, what are the elements present in this. The present day LiDAR is actually a LiDAR, or it is placed in an aeroplane. So the aeroplane keeps on moving and it can make an aerial survey of various areas on the ground. So this is taken using a LiDAR image. So it can give a very clear picture of the trees and the landscape which is present below. Laser is also used in another useful and powerful technique, which is called laser induced background spectroscopy, or LIBS. And this is used for elemental analysis or trace analysis. That means you can use it. This is a very important technique because there is absolutely no need for sample preparation. So you can use any material and simply shine a high energy laser on that, and it produces a laser induced plasma at a very high temperature. And along with that plasma, you will see the light also, which can be detected, and it can be analyzed through a spectrometer and a detector. And interestingly, the positions of the lines in this spectrum gives you what is the element present in that. And the intensity of these lines gives you the concentration of the species in this material. And this is also used for synthesis of nanomaterials nowadays, which is called lysis. So this is the technique is used. That's laser ablation synthesis in solution. So use a metal sheet or something and put it in a beaker with liquid. Then shine a powerful laser beam, nanosecond or picosecond laser beam with high energy around 600 millijoules or so. And it produces the plasma from the material, and the tiny particles emitted out of that material will be dissolved in the solution, which give you the nanomaterial generation. The most recent advances are very interesting here, and which have made photonics very useful. People are using drones and optical sensors. For example, in this picture, you see drones which are mounted with cameras or elementary LiDAR or infrared cameras or hyperspectral imaging systems. They can scan the whole landscape. So no need to have manned aircrafts to keep on imaging. So this can be used in defense and Coast Guard and other things. And this can give you precise measurement of the distance as well as the objects which are on the ground. For example, here on the left you see, this is the photograph of a railway line, and along the railway line, as you see in our bigger cities, there will be a lot of vegetation, dirty water, unhygienic material, etc. And people grow vegetables, this, that. And what kind of health hazards they are imposing, nobody is aware. So this can be surveyed using an unmanned drone with hyperspectral imaging or LiDARs or infrared cameras, and that the survey can give images like this. Here you see on the right what kind of vegetation it is, and the various different colors shown here can give you information whether it is hygienic or not. This is another picture taken somewhere in the US, Ohio. This is the blue and green region. It shows the lake water, and the neighboring area is the actual city. And here we see the green fluorescent color, which is largely due to the algae, which sometimes in some season they appear in large number, which can pose health hazards to the society. The same drones and IR cameras can take pictures like this from a distance, and these images are so precise and clear that they give you the measurements of the objects also. And suppose if there is some damage to the rail tracks, you need to replace some of the parts. You don't have to go and take measurements on this rail track, whereas you can take direct measurements from these pictures, which are very, very precise, so that the replacement and repair can be easily made. Now, this is another important thing where we keep on saying that a lot of species are being killed for various purposes due to forest fire or man-made activities or hunting, etc. So we are unable to save many important species. So in such cases, drones and infrared cameras can be used. The very interesting thing is the drones can be made to fly over the thick forests also, and these IR cameras sense the body heat of these animals, and they can give you images like this. And this can be done remotely because if you go to Amazon or other thick rainforest, the tree can go up to 90 meters. And if your drone and cameras are flying just above the trees, it can detect the moving objects like animals by sensing their body heat clearly, which are on the ground. So therefore, you can tag these species and count the species, and if they are finding, if they are being posed with some kind of danger, they can be saved also. And especially this helps, suppose if there is a forest fire, these animals can be moved to a safer place also. So here we see the picture used again by using IR cameras and drones. Again, this is done from a large distance, because here there is a combination of astronomy techniques, because in astronomy we are supposed to detect light coming from far away sources like stars and all. So these astronomers have standardized several techniques to detect weaker lights. So these techniques can be combined with our drones and IR cameras. So remotely one can survey the entire forest or deserts. You don't have to go into the thick forest where lot of animals will be there. So you don't have to go there. This survey can be done remotely, and you can keep precise watch on the animals present there. Now this is all about light that we are using in many techniques. That is, we are trying to make use of photonics for the use of society and mankind. But already in nature, there are several animals which have infrared sensors built in inside their bodies. For example, snakes, insects, fish, mosquitoes, and other animals, other creatures have natural infrared sensors which are inbuilt. You look at this beetle. So this is called a black fire beetle. And this loves fire, because wherever fire is there, it keeps on moving towards that. And it can sense fires, forest fires, which are almost nearly 100 kilometers away. So how it is done? So these beetles have sensitive infrared detectors, which are placed behind the second pair of legs. And the structure of this infrared sensor looks like this. It is called sensillum. And each sensillum can detect IR wavelengths in the range of 2.8 to 3.5 micrometers. And interestingly, these beetles can sense the forest fires from a distance of about 100 kilometers. So scientists are wondering how these beetles can detect fire forest from a distance of 100 kilometers. Because if there is a forest fire which has just started at a very long distance, we are unable to detect that. So scientists are trying to mimic or copy these techniques which are already built in the beetles, and they want to use drones with very sensitive IR cameras to detect forest fires occurring somewhere around 100 kilometers away. So they are calling these new things as beetle copters. So they can map the forest areas and locate the forest fires when they are just beginning. So you can look at this structure, the IR organ of one of the IR sensing animal. So there are about 70 sensilla. So they are quite sensitive for the IR radiation between 2.8 to 3.5 microns. Another is snakes like pit vipers and others like rattlesnakes, copperheads, etc. They have special apertures on their faces, which are called facial pits. So which make them sensitive to heat, radiation, or warm objects. So suppose if you keep a snake in a dark room and place a rat, which is its food, so it can precisely go and pick up that rat, because During daytime, it uses its eyes to locate the food, etc. Whereas during night, when there is no optical visibility, these things use the IR sensors, which are there present on their faces. So it can precisely detect 8 to 12 micrometers IR radiation, and this is the exact wavelength which is emitted by the living mice or rats or rabbits and etc. So therefore, without opening eye also, these snakes can directly go and catch their food. So this, I think, we have made an effort to bring out this kind of thing, that is application of photonics or IR sensing in animals. We have recently written an article in Kannada, which has just appeared in Vidyanagar, published by Karnataka Science and Technology Academy, which has come as an article in January, February issue. So at the end, I will just show you that. Now, hyperspectral imaging being used in food safety, another application of light. So like bacteria like E. coli or a bruise on an apple, a pesticide on tobacco leaf, and bad smell from the fish all have something in common. That is a spectral signature. That is something very particular about that. So which can be a fingerprint in the visible or invisible reflected light from them. So their presence can be detected using spectral imaging. So here we see hyperspectral imaging. It is just like a scanner, puts light and takes the image to a computer. So you can check almonds, grains, fish, chicken, etc. And this kind of imaging provides a real-time imaging on the screen, and immediately it gives information about the bacterial contamination. And if there is bacterial contamination in any part of this, then that can be easily removed before packing. Because this is very useful in the Western countries, because people use packed food most of the time. So canned food, whatever they call. So they buy from the supermarket, which is packed and kept in the market. So suppose if one of the grains is bad, then the entire can go bad. So therefore, before packing, this kind of hyperspectral imaging of the foods is done. Now this is another very important and most useful for us, because for teaching, learning, for communicating with people, we are using broadband communication, and we are using optical fiber communication, etc. Okay, so there is one particular range of frequencies, that is terahertz, 0.1 to 30 terahertz band. Okay, so just if you look at this spectrum, once again I'll show you. So here we see visible to visible range, and next to visible we have infrared range, and below that you can see 10 to the power of 12, that is a frequency that is called the terahertz range. Okay, and on the left you see radio waves, microwaves, which have been used as the most powerful frequencies for communication, wired communication, like the earlier telephones, etc., and radio communication, television communication, etc. So they all go up to 10 to the power of 9, 10, or 11. Okay, and on the right side, you see we have visible, ultraviolet, X-ray, gamma rays, etc. Okay, these are all high energy radiation. So these are all optical radiation. So optical, the scientists who are working in this optical radiation, they think that this terahertz or infrared is containing weak photons. Whereas these radio waves and microwaves, that is electronics people, they want to come into this infrared range because the frequency is quite high compared to micro and radio waves. And the most important thing is, once you increase the frequency, the data carrying capacity of the system increases. So therefore, communication people want to get into that. Okay, so therefore terahertz band is useful in developing future smart cars and navigation. For example, in our country, we are using internet at the speed of, let us say, nearly 1 Gbps. So I suppose most of the time we get 100 Mbps. So you may be wondering to know the speed of internet at the NASA in US is 91 Gbps. So that's quite fast. So as we know, we have Wi-Fi or wireless fidelity. Now the next generation communication is Li-Fi or light fidelity. There is a spelling mistake here. It is FIDE only, not A. Okay, so this is a transmission of data through illumination. So you can use LED source or some IR laser diode source. So data is transmitted through IR radiation. That is, we are using terahertz band. And the advantage of Li-Fi as compared to Wi-Fi is it is totally secure. Now, if you have Wi-Fi communication at home, and if your internet is not locked by any password, anybody in your anybody like your neighbors or those people who are moving around your house can make use of that unless you put a password. But this Li-Fi is just like a LED bulb which can be placed at one corner, and the systems under that LED only will get the internet connection, but of course with very, very high data carrying capacity. Okay, so beyond that, so if the light is not visible to your system, then it is not available. That means anybody outside your homes or offices cannot make use of this data. And frequency of operation is at least 10,000 times frequency of the spectrum of radio, because we were up to gigahertz and now we are going to terahertz, means at least 10 to the power 12 to 14 we are moving. So therefore, it is our 5 orders of magnitude higher than the radio wave communication. So essentially data carrying capacity also increases. You can transmit large amount of data with efficient transfer. Okay, so these are the things I already said. So this is an imaginary network. In future, this kind of thing may come. So we can see that we have 5G link denoted by green light, terahertz link denoted by purple, and Li-Fi link by yellow. So that means cars can communicate with each other, and cars can communicate with the towers Wi-Fi, and the cars can also communicate with the traffic lights. So if there is a red light, the car can automatically stop at certain distance. So though all these will be pilotless cars, and these are slowly coming in the Western countries. So you don't have a driver and you don't have to drive. So you and your family can sit and relax and do the work and program the car to go to a certain destination. It will take you there. So it will communicate with the signals to the towers placed at various places, as well as in between the two cars, because they can avoid accidents and safely one can go to desired destination. So these are the things which are using all terahertz and light fidelity systems. So this is an example of a Li-Fi system which was installed in an island, so in the UK. So this island was having hardly about 30 families here, and all these 30 families were not able to get internet communication because of the bad weather and other things. So recently there was a Li-Fi system which was fixed inside this lighthouse, and it was communicating to all the 30 families. Okay. And now, because of this Li-Fi system, there is absolutely no disturbance in the internet, and all the families and members are using internet without any break. So there is some company called Signify, which has installed Li-Fi systems in the aeroplanes, buses and other things, with all touch screen and other things. This is an artist's imagination of laser communication relay demonstration to be launched in 2021. I really not aware whether it has been launched or not. This is another thing, that is Li-Fi system using a laser being hosted underwater, that is under the sea. Just for your information, in 1958, the first integrated chip with a memory of 1 bit was developed. And now in 2021, latest advanced ICs are made by extreme ultraviolet laser lithography using 195 nanometer carbon dioxide laser. Okay, and the memory is also quite high. And use of light in archaeological applications. So you can use lasers to clean the marble structures. Okay, so this is one of such pictures. You that cleaning the Capitol building. You can use but for cleaning your Taj Mahal or any other architectural wonders. So light can be used for many applications. So this is one of the recent articles which has come in Vidyanagar, January, February issue. So we have made an effort to put this in Kannada, all the latest advances in photonics for the use of high school and students who are learning science in Kannada. So this is our laboratory where we have picosecond laser and the detection system. This is the argon ion laser used for Raman spectroscopy. So this is the beam from, as I mentioned, this is the 514.5 nanometer green laser beam from argon ion laser in our lab. And this is my team. These are all my students. This is Mallikarjun Patil, who has completed doctorate degree recently. Shivraj Patil, Prajakta, they have just submitted their thesis. And Tilak Raj, Vigneshwar Bhatt, Vikram Pujari, Sri Krupa, and Altaf Hussain, they are all working right now. And Dr. Manjunath Wari and Sarnaikar, they have completed a couple of years ago and working as teaching assistants in our department. And thank you so much for your patient listening. Thank you very much. Hello.
Thank you so much, sir. Thank you so much.
If there are any questions?
Yes, sir. Now the time is to have an interaction with the resource person. I request the participants to ask the questions, please. Please raise the hand. I will unmute yourself, and so that you can interact with the sir. Please. Please raise the hand so that I can come to know. Arvind Mishra, are you interested to ask the question? Yes, yes. You can talk to sir. Arvind Mishra. Hello.
Hello.
Hi, you can speak with the sir. Arvind Mishra. Okay, Thala.
Yeah, I do not hear anything.
Hello, Arvind Mishra. Okay, I think Thala is asking the question. Yes, you can unmute yourself and you can ask the question. Thala.
Hello. If they can write also, we can look at that.
Yes, sir. Yes, sir. Yes, sir. You can write in the chat box so that sir can see the question. Okay, sir. Sir,
So
myself,
it was, yeah,
Santosh.
tell me.
Sir, how this the photonics can be used in the Tesla car? Nowadays, the Tesla car is using the electromagnetic radiation for auto driving, sir.
Hmm, hmm.
How it is used, sir? How this
Yeah,
photonics is related to that?
yeah, autopilot. I hear that they are bringing autopilot cars, and autopilot
Yeah.
cars again, they are supposed
Yes,
to be
sir.
programmed, and they are, as I mentioned in the last picture here. 1 second. So this is exactly, that's what they are trying to do, because
Yes,
the
sir.
cars will be able to communicate with each other, because there is no driver who can monitor the oncoming car or any
Yes, sir.
car that follows you. So
Yes.
in order to avoid accidents and other things and safe passage, so cars need to communicate with each other. Okay, and
Yes.
they need also to communicate with the tower
Yes,
for
sir.
the, like your GPS. So they need to plan the route, etc. And also they need to contact or make communication with the traffic signals,
Yes, sir.
because at the traffic signals, as per the signal the color, that is red or green, they are supposed to stop or pass through. So all these communications will be done by Li-Fi systems. Okay,
Yes, sir.
Li-Fi as well as now, although this is mentioned here 5G link, people are already working on 6G link that will be much faster and quite efficient communication system. So that's what they are planning to use.
Yes, sir. Yes.
Yeah.
So one more question, sir. Is there any side effect on the animals whenever we are tracking with the lights, sir?
Oh, absolutely no, because IR will not damage you.
Yes.
Okay, and these IR detectors will be actually, suppose if you are surveying, if you are talking of survey of animals in the forest,
Yes.
then these cameras are detecting IR radiation from the animals. That is the body heat. IR radiation is nothing but the body heat generated by the animals.
Yes.
So detector looks for the light coming from the body of the animal. So there is absolutely no light going and damaging the animals.
Yes. Just like
Okay.
contactless thermometer. Nowadays we are
Yeah,
using.
exactly. Yeah, exactly.
Contactless
That's
thermometer.
probably that's the right example.
Yes, sir. Thank you, sir.
Okay, yeah. So
Thank you, sir.
there can't be any harm.
Yes, sir. Yes, sir.
Yeah,
Thank you, sir. Thank you, sir.
yeah.
Participants, if you have any questions, please. Yes, sir. We are about to conclude the session, sir.
Sure.
Now I request Dr. Seema yes, Kamlapur Madam to propose vote of thanks. Over to Kamlapur Madam.
Hello.
Yes, sir.
Yeah. Hello. There is no audio. Hello.
Audio is there, sir. Yes, sir.
But I'm not hearing anything.
1 second, sir. 1 second.
Good evening, sir.
Yeah, good evening. Good evening. How are you?
I'm good, sir.
Yeah.
Sir, good evening, sir. And
Yeah.
good evening to principal, sir, dear colleagues, students, and everyone who attended the seminar. It's my privilege to propose a vote of thanks and acknowledge the contribution of those who really worked hard to make this event possible. Management KLE Society, PC Jabin Science College, and the entire fraternity of the institution, extend my sincere thanks to Dr. Sanjeev Inamdar sir for accepting our invitation and making this grand success. Today, we had an opportunity to hear your lecture, and this will surely encourage us in all our future endeavors. Thank you, sir. Thank you so much.
Thank you.
I
Thank you very much.
also thank our respected principal, Dr. L.D. Hokeri sir, for encouraging and supporting us for organizing such an event. I thank Chairman, PG Department of Studies and Research in Physics, Dr. P.R. Jigal sir, and Dr. Abhi Pooja sir for guiding and making this event grand success. Finally, I would like to thank to all the students, participants, and UG physics faculties for attending the seminar and making it a grand success. Thank you, one and all. Thank you, sir.
Yeah, thank you so much for inviting me. And I thank Professor Harkeri and all the staff and students for attending this seminar. Thank you so much. Thank you.
Yes, sir. Thank you, sir.
Thank you. Thank you very much.
Thank you all, Uma Madam, from other colleges, and from Dr. Sudhir Hiramat, and my colleagues and my students, and those who attended from other colleges and other states, and the students of Inamdar sir, and all. Thank you, one and all. Thank you, sir.
Thank you. Thank you so much.
Yes. Now I will send the feedback link. Please fill the feedback link, all.